High-density IT hardware generates enormous amounts of thermal energy. The central engineering challenge of any modern data center is guaranteeing that every single joule of that heat is reliably extracted and removed from the facility without ever violating strict environmental operating limits. To achieve this, we rely on the first core axiom of data center MVAC design. The thermodynamic chain is an absolute unbroken path from the heat source to final rejection. This path cannot be estimated. It must be precisely mapped and mathematically accounted for. This schematic illustrates the foundational concept of the cooling boundary. Notice the glowing blue dotted line enclosing the thermal-controlled space. The rule here is rigid. Only heat sources physically located inside this specific boundary are factored into the facility's base cooling load. Within this space, we calculate several distinct heat gains. We account for the IT equipment itself, internal electrical losses from switchboards and UPS systems, ambient lighting, body heat from facility personnel, envelope infiltration, and any process or liquid cooling interfaces. Once the present governing duty is established, we calculate the final design cooling load by applying an approved growth factor. Here, a 2 megawatt IT load basis is multiplied by a 10% future growth allowance for high-performance computing, bringing the total design requirement to 2.20 megawatts. There is an inflexible rule when sizing this load. As noted in the yellow warning box, redundancy factors and operating margins are verified completely separately. They are never added to the base heat calculation. An ambiguous thermal boundary guarantees systemic failure. If the initial load basis is flawed, every downstream pipe, pump, and chiller is compromised before a single server is powered on. Once the thermodynamic load is mathematically defined, we move to the physical reality of extracting that heat from the IT racks. This diagram maps two primary capture architectures. Look at the top section labeled Path A, illustrating traditional air cooling. Hot aisle exhaust is drawn into the computer room air handler, or C-rack. Inside the unit, fan wall coils absorb the sensible heat, transferring it directly into the facility's hydronic loop. The volume of air required for this process is strictly tethered to the laws of physics. If the sensible heat load spikes, the required airflow volume must increase proportionally to maintain temperature equilibrium, assuming air density and specific heat capacity remain constant. High-density AI deployments require a different approach. The lower section outlines Path B, direct-to-chip liquid cooling. Here, a secondary liquid coolant flows directly over the cold plates on the chips themselves, capturing heat at the source before traveling to a rack manifold. The critical component in this path is the cooling distribution unit. It acts as a liquid-to-liquid heat exchanger, completely isolating the secondary rack loop from the primary facility water. The CDU operates with its own redundant pumps and stringent leak detection systems to protect the hardware. Despite their different physical mechanisms, both the air and liquid capture architectures share the exact same objective, moving the thermal load out of the data hall and safely into the facility's central hydronic loop. The efficiency of this initial heat capture directly dictates the flow rates, pipe sizing, and pressure demands required for the entire downstream transport network. The hydronic loop is the circulatory system of the data center. Its sole purpose is to transport massive volumes of capture heat over long distances, moving energy from the white space out to the mechanical plant. This schematic details a primary variable flow chilled water loop. We trace the closed circuit from the modular air-cooled chiller through the variable speed duty pumps, out to the remote CRAW terminal units, and back again. Sizing the pumps requires calculating the closed loop pump head. A strict engineering rule here is that static lift is not added to the calculation. Because the system is a closed loop, energy is only expended to overcome the friction of the pipes and the pressure drops across the equipment. During low load scenarios, the chillers require a guaranteed baseline of water volume to prevent freezing and mechanical damage. The flow meter communicates with a bypass controller, which automatically modulates the minimum flow bypass valve to maintain this minimum requirement. Simultaneously, a remote differential pressure sensor located across the furthest CRA coil dictates the speed of the variable speed pumps. If this sensor detects a pressure drop that cannot be recovered by the duty pump, it automatically triggers the standby pump to start. This pressurized network functions as a dynamic environment, balancing its mechanical output against the fluctuating thermal demands of the IT load. Following the hydronic loop outside the building brings us to the cooling plant. This 3D layout illustrates the final stage of the thermodynamic chain, rejecting the collected heat into the ambient atmosphere using chillers and cooling towers. The heat rejection equation defines the total thermal burden on the mechanical plant. External condensers dissipate the primary cooling load from the IT racks, along with the supplemental heat generated by the compressors themselves. To verify that this entire process is operating efficiently, we rely on a chiller plant optimizing system. This dashboard tracks real-time key performance indicators, such as rack inlet compliance and available capacity margin, providing the raw data needed to monitor system performance. One of the most heavily scrutinized metrics is power usage effectiveness. Calculating an accurate PUE requires synchronized meters and explicitly declared boundaries, comparing the total facility energy input against the isolated IT energy consumption at the UPS output. A major threat to this efficiency is low delta T syndrome. If the temperature gap between the chilled water supply and return shrinks, the system attempts to compensate by forcing excess water through the pipes. This causes pump power consumption to skyrocket exponentially, eroding both efficiency and available capacity. Operational efficiency claims are meaningless without the underlying data. Strict meter boundaries and time-aligned evidence from the control system are the only ways to validate those claims. Optimal, steady-state design is only half the equation. The second foundational axiom of data center engineering is that a resilient architecture is judged entirely by its behavior during catastrophic failure or deep maintenance. This schematic details the principle of failure domain independence. A resilient system ensures that power sources, control networks, hydronic distribution piping, and ambient rejection paths never share a single point of failure. This strict separation enables concurrent maintenance. This is the operational capability to completely isolate any individual asset, whether it's a primary chiller, a circulation pump, or a piping branch, without ever violating the required cooling duty supplied to the IT load. In this concurrent maintenance scenario, Train A has been isolated and drained for service, indicated in orange. Because the failure domains are independent, Train B remains online and automatically ramps up its output to carry the facility's required thermal load. The greatest threat to this independence is a common mode failure. Shared water headers, unified cyber networks, or improper manual overrides by personnel can bridge these independent domains, taking down both trains simultaneously. To mitigate this risk, piping crossties between independent trains are strictly controlled. They utilize motorized isolation valves that are normally closed and are only permitted to open under highly scrutinized, pre-approved automated sequences. Simply having extra cooling capacity does not equal redundancy. True resilience requires the strict physical and logical separation of every critical cooling path. When a failure breaches these domains, the system relies on automated emergency logic. If the optimization system detects a critical condition, like the sudden loss of a primary cooling source, it executes a predefined response matrix instantly. In any crisis, the absolute first rule applies: stabilize thermal service to protect the IT load. Diagnosis happens only after the hardware is safe. This sequence diagram maps those automated responses. If a low differential pressure alarm is validated at step F1, the system automatically isolates the failed asset at F2 and starts the standby path at F3. A high IT inlet temperature alarm will immediately force a suspension of all non-essential maintenance. These sequences are governed by the hold point philosophy. This is a strict operational mandate, instructing engineers to immediately stop all action if physical safety, the validity of sensor data, or the facility's residual capacity is ever in doubt. Ultimately, these emergency responses are verified through a rigorous commissioning lifecycle. We execute controlled loss of source scenarios during integrated systems testing to prove that the design intent functions under real-world stress. An emergency event is not over when the temperature stabilizes. The system must pass a strict restoration gate. Normal mechanical lineups are confirmed, manual overrides are closed, standby assets are verified available, and all time-aligned evidence is signed and archived. A resilient cooling system exists only if proven under stress. Without auditable, time-aligned evidence demonstrating recovery, thermal design intent is just a theory.